You clicked because you are wondering why adding more GPUs stops working for next token prediction tasks. The real problem is that your hardware cannot keep up with the memory demands of this specific paradigm as models grow larger. You will discover exactly where the bottleneck lies and why specialized silicon might be the only way forward to break through these limits. For years, we have operated under a simple assumption in artificial intelligence. If you throw enough raw compute at next token prediction, eventually you get human-level reasoning. We assumed that scaling laws would carry us indefinitely because the algorithm itself was sound. The prevailing argument suggests that if current architectures cannot handle larger models or longer sequences, it is simply a matter of throwing more parallel processing power at the problem until the math works out. But recent research indicates we are hitting a computational ceiling not due to flaws in the algorithm, but because our hardware architecture is fundamentally mismatched with what next token prediction actually requires. Here is the thing that changes everything about how you should think about scaling large language models. Standard autoregressive training relies on teacher forcing, which creates a severe inefficiency when sequence lengths increase. As you generate each token one by one, the system must repeatedly fetch the same key value cache from memory for every single step in the generation process. This means that as your sequences get longer, the ratio of useful computation to necessary memory access collapses rapidly. The GPUs are forced to spend more time waiting for data than actually performing calculations because they must constantly pull the state of previous tokens into fast memory before processing the next one. This creates a scenario where massive parallelism becomes ineffective rather than helpful. Modern graphics processing units are optimized for matrix multiplication, excelling at doing billions of operations simultaneously when all inputs are available at once. However, next token prediction is inherently sequential because each new token depends entirely on the history generated so far. The critical path in this workflow is determined by the slowest memory access rather than raw floating point performance. You cannot parallelize a process where Step 2 must wait for Step 1 to finish reading from the database before it can even begin its calculation. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider what happens when you try to scale long-horizon reasoning tasks on current silicon. The system hits a wall not because the model architecture is broken, but because the memory bandwidth required to feed tokens sequentially exceeds the throughput of our parallel architectures. We are trying to force a sequential problem onto hardware designed for massive parallelism without accounting for the latency constraints involved in retrieving data at every single step. This mismatch means that adding more GPUs often results in diminishing returns where you get less performance gain per dollar spent as the system becomes increasingly bottlenecked by memory traffic rather than compute power. Now consider this insight from recent studies on training paradigms beyond standard prediction. While some researchers point to algorithmic limitations like teacher forcing failing to capture long-range dependencies, others argue that even if we fix those issues, we still face a hard physical constraint. The evidence suggests that hybrid approaches such as diffusion forcing can outperform pure next token prediction on complex planning tasks by optimizing the full sequence simultaneously rather than step by step. These methods allow models to explore multiple reasoning paths and backtrack when necessary, addressing what some call the cautiousness gap, where current systems struggle to explore alternatives before committing to a single path. However, these advanced techniques are currently impractical for widespread deployment on standard graphics cards due to high latency overheads that make them too slow for real-time use. The computational cost of evaluating multiple future states simultaneously is simply too heavy for the memory bandwidth available in current consumer and enterprise-grade accelerators. This suggests a critical realization. We may be hitting a wall not because the training objective itself is suboptimal, but because our hardware cannot support the efficient execution of these superior algorithms without fundamental architectural changes. The gap between what is theoretically possible with new training objectives and what is practically achievable on existing silicon reveals why simply rearranging token prediction orders or integrating future condition sampling does not solve the scaling problem in isolation. While multi-token prediction methods show promise, they introduce substantial complexity that current parallel architectures cannot amortize efficiently without custom interconnects designed for simultaneous generation. This implies that the path to breaking through the current ceiling requires a shift towards specialized application-specific integrated circuits rather than just better software optimization on general-purpose hardware. Practitioners note that while alternative methods like diffusion hybrids show superior benchmark results in planning and video generation, they introduce substantial complexity in data augmentation and inference latency, which makes them difficult to deploy at scale today. Consequently, the debate over whether we need algorithmic evolution or hardware specialization remains unresolved because no one has quantified the exact computational cost of these new non-autoregressive training paradigms compared to current standards on existing silicon. We are essentially flying blind when trying to determine if a specialized chip would actually solve the problem or just add another layer of complexity without delivering proportional gains in performance per watt. The critical knowledge gap lies in determining whether the bottleneck is truly hardware-bound or algorithmically bound, as this decision dictates where we should invest our engineering resources for the next decade of artificial intelligence development. If we continue to pour billions into larger GPU clusters while ignoring the fundamental mismatch between sequential memory access patterns and parallel compute units, we will simply hit a wall faster than anticipated with no clear path forward. The future likely belongs not to those who can build bigger clusters, but to those who design accelerators specifically optimized for the unique latency constraints of next token prediction and its evolving successors. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.